Hey, geometry students. In this lesson, we're going to be talking about circles and something that we can do inside a circle. We can inscribe angles. And then, because we're talking about inscribed angles, and one of the most common figures that we use with angles is a triangle, we're going to be specifically talking about inscribed angles in triangles in this lesson as well. We're going to start off with the definition of what an inscribed angle is. It's an angle whose vertex is on a circle and whose sides are chords of the circle. I'm going to show you a figure that sort of compares what an inscribed angle is to angles that we've considered in a circle before. We have been considering central angles in a circle. So you see the 64-degree angle right here? That's what's called a central angle. And a central angle has as its vertex the center of the circle. We know some properties of central angles. We know that the central angle is going to open up to the outside of the circle in such a way that this inner angle is 64 degrees, and 64 degrees of arc is swept out between M and O on the outside of the circle. Now, we're not going to be talking about this central angle in this lesson. We're going to be talking about an inscribed angle. An inscribed angle is where our vertex is on the circle, and then the sides of the angle are chords of the circle, which means that the sides go across the circle to the other side. This particular inscribed angle is a little special because one of the sides is a diameter, but that doesn't have to be true of every inscribed angle. All that has to be true is that the sides are chords. So this NM, which is now NPM, it passes through P, but NM could go up here and it would still be an inscribed angle. Now, we're going to specify also what an inscribed triangle is because, again, that's a very important figure that we've been working with. When we can inscribe angles, we could also put triangles inside circles as well. And I want to point out as well, this is not an inscribed triangle right here. There's a triangle in this figure that is not an inscribed triangle. Now, pay attention to the definition of inscribed triangle. See why this is not meeting that definition. It's a triangle whose vertices are on a circle. And then the sides of an inscribed triangle are chords of the circle. Vertex N is on the circle, vertex O is on the circle, but see how vertex P is the center of the circle? It's not on the circle. This would not be an inscribed triangle. However, if I drew a chord from O to M, then the triangle MNO would be an inscribed triangle because all the vertices are on the circle and the sides are chords. Notice that NP is a radius, not a chord. OP is a radius, not a chord. Okay? And then when we talk about intercepted arc, the intercepted arc is the arc formed by an inscribed angle. So of the angle MNO, which is an inscribed angle, the intercepted arc would be arc MO right here. The arc formed where the two sides of that the inscribed angle meet the other side of the circle. There, it forms an arc that is our intercepted arc. Now that we have these terms down, let's talk about a few theorems related to these inscribed angles. The first theorem, theorem 47.1, states that the measure of an inscribed angle is equal to half the measure of its intercepted arc. So if I were to measure this angle as angle X, the intercepted arc here would be 2 times the value of this angle. Another way of saying it is the measure of angle PRQ, this angle here, is 1/2 the measure of PQ. And over here, I know that MO has to be 64 degrees because the central angle always is the same, has the same angle as the arc that it draws on the outside of the circle. Well, that means that MNO would have to be 32 degrees. It's going to be half of this amount. All right, that's our first theorem. Our second theorem, if an inscribed angle intercepts a semicircle, we're going to talk about what that means in just a second. So intercepts a semicircle. If we look at this inscribed angle here, uh, what's the intercepted angle? Well, it's exactly half of the circle. If that's true, then the inscribed angle is a right angle. If it intercepts a semicircle, it's a right angle. This one's one you just got to remember, and it's kind of tricky to remember, so you need to keep this in mind. So you see that angle DEF intercepts a semicircle. Now, how is it going to intercept a semicircle? The only way it's going to do that is if, when I look at this triangle, okay, if I were to look at the third side of the triangle, the inscribed triangle made by my inscribed angle, the third side is going to be a diameter. So one of the sides of the inscribed triangle is a diameter of a circle, then it's going to be a right triangle. So if we're intercepting a semicircle, hey, why does that have to be? Well, think about this for a second. A semicircle has 180 degrees. What's half of 180 degrees? 90 degrees. Boom. All right, let's take a look at this next one. If two inscribed angles intercept the same arc, then they are congruent. If you ever see this figure inside, kind of like a weird distorted hourglass, if you ever see this figure inside a circle, what you're probably looking at is two separate inscribed angles, ACB, ADB. And if they intercept the same arc, they have to be the same size because this arc size is related to the angle size. This angle is going to be half of this arc size, and this angle is going to be half of this arc size, so they have to be the same. And then lastly, if a quadrilateral is inscribed in a circle, then it has supplementary opposite angles. So angle M and angle O, if I add them together, are 180 degrees. Angle P and angle N are 180 degrees. That's a theorem that can be proven as well. We're going to worry about that later. Right now, we're going to just use these theorems to solve some problems in the next video.